Universal law of gravitation. According to this law, the force of attraction between two particles or two bodies is directly proportional to the product of their masses and inversely proportional to the square of distance between them. Suppose we consider two bodies A and B having masses m1 and m2 respectively. Let the distance between these two bodies is r, and according to law of gravitation, the force of attraction F, or force of gravitation between the bodies, this is directly proportional to the product of masses, that is F proportional to m1 m2, and is inversely proportional to the square of distance between them, that is F proportional to 1 by r square. Combining these two equations, we get F proportional to m1 m2 by r square, or we can write this as F equal to G into m1 m2 by r square. This G is called universal gravitational constant. This is the mathematical form of Newton's law of gravitation. In this formula, the magnitude of force, this varies inversely with the square of the distance between the two particles. Hence, it is called inverse square law. According to this, force of gravitation is directly proportional to 1 by r square, where r is the distance between these two particles. The value of G is 6.67 into 10 power minus 11 Newton meter square per kg square. This is in SI, and G is called universal gravitational constant. We can define G as the force between two objects having unit mass separated by unit distance. In this formula, if we consider m1 equal to m2 equal to 1 kg, r equal to 1 meter, then we get G equal to F. That is, the value of universal gravitational constant is nothing but the force between two unit masses separated by unit distance. Let us consider the force between two masses m1 and m2, which are separated by a distance r, is F. That is F equal to G m1 m2 by r square. If the distance is doubled, then what happens? Yes, the force is directly proportional to 1 by r square. If the distance is doubled, F prime proportional to 1 by 2r square, then new force becomes 1 by 4th of initial force. That is, if the distance between two particles is doubled, the gravitational force becomes 1/4. If the distance between the particles is halved, then what happens to gravitational force? F proportional to 1 by r square. When the distance is halved, that is, it becomes r by 2, then F prime is directly proportional to 1 by r by 2 whole square. Now F prime by F, this is nothing but 4r square by r square, or 4. That is, when the distance between the two particles is halved, the gravitational force becomes 4 times. F equal to G into m1 m2 by r square. This G is called universal gravitational constant. The importance of universal law of gravitation is the gravitational force is one of the fundamental force in nature, and this is responsible for solar system, that is motion of planets around the sun, holding the atmosphere near the surface of the earth, the flow of water in rivers, for rainfall and snowfall, motion of the moon around the earth. Because of gravitation only, the tides will occur, and it helps us in prediction about solar and lunar eclipses. The universe exists because of this gravitation, or without gravitation, there is no universe. The characteristics of gravitational force. The gravitational force between two bodies or objects does not need any contact between them. That means it is an action at a distance. Gravitational force between two bodies varies inversely proportional to the square of the distance between them. Hence, gravitational force is an inverse square law. And gravitational force between two bodies or objects is an action-reaction pair. Suppose we consider two masses A and B. On this mass, a gravitational force is acting due to mass B. Similarly, on B, a gravitational force is acting due to A. And these two are equal and opposite in direction. That is, we can write F1 equal to minus F2, where F1 is force on B due to A and F2 is force on A due to B. And using this formula F equal to G into M1 M2 by R square, we can find the gravitational force acting between any two masses. And one more characteristics of gravitational forces, it is independent of medium present between the masses. That means, suppose we consider two masses m1 and m2 in air. Let us consider F as the gravitational force acting between them. If the same masses are taken in water, then also the gravitational force between them is same. It is independent of nature of material that present between the masses. Now let us try to understand what is the acceleration due to gravity. According to Newton's third law, to every action, there is always an equal and opposite reaction. That means, if an object A exerts some force on another object B, then the object B exerts equal and opposite force on object A at the same instant. This law applies to the force of gravitation also. Suppose we consider an object of mass m, small m, is at some distance from the earth as are seen in the figure. And between these two masses, the gravitational force is acting. The force on this object due to earth is equal to the force on the earth due to this object. And these two forces are equal and opposite in magnitude. And because of these forces, the body will get acceleration. We know that force is equal to mass into acceleration. And because of this force, the mass gets the acceleration. At the same time, earth also get acceleration. But the mass of the earth is very huge. In this equation F equal to ma, m is very large. There is no change in F. Then what about A? The acceleration of earth is very small, but the acceleration of this body is more, and it moves with some acceleration towards the earth. The acceleration gained by this body due to attractive force of the earth or due to gravitational force, it is called acceleration due to gravity, and the value of acceleration due to gravity is 9.8 meter per second square. This is acceleration due to gravity. Now let us try to derive an expression for acceleration due to gravity of the earth. Consider an object of mass m on the surface of the earth. Let capital M is the mass of the earth, capital R is the radius of the earth. In this case, the object is at a distance r from the center of the earth. The gravitational force between the mass and object is F equal to G into small m capital M by R square, where small m is mass of the object, capital M is mass of the earth. R is the distance between the center of these two objects. If G is acceleration due to gravity, the weight of the object is given by F equal to mg. This is acting vertically down. This is the gravitational force due to earth on the object. And this is nothing but the gravitational force acting between two objects. Therefore, we can write m into g is equal to gmm by r square, or small g equal to g into capital M divided by capital R, where capital M is the mass of the earth, capital R is the radius of the earth, and this is the acceleration due to gravity on surface of the earth. Now, using this equation, we can find the acceleration due to gravity on the surface of any planet. Now the question is, the value of G is same at all places? The value of G varies from place to place on Earth, and also it varies from planet to planet. The value of G depends on the mass of the planet and radius of the planet. If you go for Moon, since the mass and radius of the Moon are less compared to Earth, automatically the value of G, that is acceleration due to gravity, on Moon is less compared to Earth. If you go for Jupiter, mass, radius of Jupiter are more compared to Earth. Therefore, the acceleration due to gravity on Jupiter is more compared to Earth. Then what about Sun? Sun is very large compared to Earth. Therefore, the value of acceleration due to gravity on Sun is very huge compared to Earth. Within a planet also, the value of G varies with the shape of the planet. We know that the acceleration due to gravity g is given by gm by r square, and the expression for g calculated by considering the Earth as a spherical body. But Earth is not a perfect sphere. It is in elliptical shape as we are seeing in the figure. Therefore, the radius of the Earth is not constant throughout. The value of g is different at different positions. The equatorial radius of the Earth is high compared to polar radius. Therefore, at equator, the value of g is g equal to gm by re square, and at poles, the value of g is gp equal to gm by rp square. Therefore, gp by ge, that is acceleration due to gravity at poles to acceleration due to gravity at equator, this is equal to re by rp whole square. Already we know that Re greater than Rp. Therefore, Gp greater than Ge. Therefore, the value of G is more at poles compared to equator. As we move from equator to poles, the value of G increases. It is maximum at poles, minimum at equator. Suppose we weigh 1 kg of sugar at equator as well as at poles. Where we get more amount of sugar, at equator or at poles? Just you think about this question. Now we discuss about a variation of value of g with height. We know that the acceleration due to gravity on the surface of the earth is given by g equal to gm by r square, where r is the radius of the earth, m is mass, and g is universal gravitational constant. Now what is the value of g at height h from the surface? This is nothing but gm by r plus h whole square. Now from these two equations we can write gh by g, this is equal to gm by r plus h whole square into r square by gm, that is gh by g, this is equal to r by r plus h whole square. R plus h is greater compared to r. gh by g is less than 1. gh by g equal to r by r plus h whole square. This is the relation between the value of acceleration due to gravity at height h and on Earth's surface. If the value of h is very small, now this can be written as gh. This is equal to g into 1 by 1 plus h by r whole square, and using mathematical relations, we can write this as gh is equal to g into 1 minus 2h by r. If the value of h is very small, if the value of h is very less compared to the radius of the earth, then we can apply this formula. And now we discuss about variation in the value of g with the depth below the surface of the earth. On the surface of the earth, the value of acceleration due to gravity, this is given by g equal to gm by r square. If we consider earth is a sphere, writing mass is equal to volume into density, this can be written as g into 4 by 3 pi r cube small d divided by r square. Here r is the radius of the earth, d is the density of the earth. Now this is equal to g into 4 by 3 pi r d. Now the acceleration due to gravity at some depth h, this is given by g into 4 by 3 pi r minus h into d. At g equal to gm by r square, capital M is mass of the earth, capital R is the radius. When we go into depth h, at this position, the value of g is due to the sphere within this radius r minus d. Therefore, at this position, the mass is different. Hence here we are writing mass in terms of density. Now from these two equations we can write gd divided by g, this is equal to g into 4 by 3 pi r minus h into d divided by g into 4 by 3 pi rd, or this is equal to r minus h by r, or the acceleration due to gravity at the depth h is gd equal to g into 1 minus h by r. As r minus h by r less than 1, we can say the value of gd is less compared to g. That means as we are moving into the earth, the value of g decreases. Similarly, as we move up from the earth, then also the value of g decreases. At the center of the earth, h is equal to r and acceleration due to gravity becomes 0. This is about the variation of acceleration due to gravity with depth.